Hello everyone. Today we're going to learn about solving systems of equations in three variables, though what we learn now is going to be able to be applied to systems of equations with more than three variables. Now, let's look at an example. Now, the first thing to remember is if we're solving for three variables, we need at least three equations. If we're solving for two variables, we need at least two equations, and so on for a larger number of variables. So the number of variables is equal to the number of equations. Another point to keep in mind is trying to line up your variables neatly, like this, so that all the r's are in line, all the s's are in line, and all the t's are in one line. Makes it a lot easier to solve for the solution. Just a tip. Okay, now, what is the solution? We learned what the solution is. The solution is the specific value for all three of these variables that will make all three of these equations true. So it would be the value for r, s, and t, which would hold for all three equations. When we solve for systems of equations with two equations, and we were looking at an xy plane, we would graph the first equation, and we would graph the second equation, and we would look for the point where those two equations met. That would be the solution. We can extend the same thing to three equations. If we think of a 3D plane, or 3D space, we have x, we have y, and we have z. So, when we're solving for systems of equations in three variables, what we're doing is we're graphing the lines that those equations represent in a 3D space, and we're looking to see for the point where those lines all intersect, if there is one. Since there are three lines here, there are several cases possible. When we only had two variables, and we had two lines, there were only two cases possible. Either the lines intersected at some point, a single point, and there would be a solution, or the lines were parallel to each other, and there was no solution because the lines would never intersect. Another example of no solution would be if the equations just describe the same line. For example, if one equation was a multiple of the other. And then we would have infinite solutions. Because any answer that would be true for one equation would also hold for the other equation, since they're the same equation. Now, when we extend this to three variables, we only consider a system to have a solution if all three lines intersect at a single point. Otherwise, we could have a system where, say, all three lines are parallel. That would be no solution. Or we could have a system where two lines are parallel and another line intersects across both of them. We still say this is no solution, or more precisely, not a unique solution. Or we could have a case where the lines aren't parallel, but they still never intersect, because it's a 3D space. So one line could be moving this way, another line could be moving in this way, but on top of the other line, so that they never actually intersect. Another line could be moving this way behind the other two lines. Now, the details of this aren't important at this stage. What we need to know is that it's only a solution if all the equations intersect. So let's look back at our example. Can we find a unique solution for these three lines just by looking at the three equations we have here? If we look closely, it appears that the first equation is just a multiple of the second equation. It's 2 times the second equation. That means if we were to graph this, we would get a graph that looks something like this, where we have a line, a random line, and that's the second equation. And the first equation is the exact same line. And then the third equation is a different line somewhere else. Over here, we would have infinite solutions because the first equation and the second equation describe the same line. So any r, s, and t value which satisfy the first equation would also satisfy the second equation, and vice versa. So we say this has infinite solutions. So, to revise, systems of equations have a unique solution if they meet at a single point, such as here. They have no solution if they never meet. So this has no solution. And finally, in this case, we have infinite solutions because the equations describe the same line. Also, don't forget that the number of variables has to equal the number of equations that you have. Alright, see you next time.